And now we'll move on to the next talk, which is Fred Davies, small-scale structure of the pre-reionization IGM in greater proximity zones. Fred, go ahead.
All right, sure. Is this coming through? Can you hear me?
Yep, perfect.
Perfect. Okay, yeah, I'd like to tell everyone about this project I've been working on for a little while now with Joe Hanawi, my former boss, on how we can use the proximity zones of the highest redshift quasars, so the ones pushing really deep into reionization, to probe some physics of the early pre-reionization IGM. All right, so why should we care about the small-scale structure of the IGM? Well, it's been known for quite a while that the small-scale structure of the IGM is very sensitive to cosmology, like the nature of dark matter, for example. So here I'm showing a few slices of cosmological or volume renderings of cosmological simulations with hot, warm, and our favorite cold dark matter. And you can see that as you go from hot to cold, that due to the fact that the free streaming scale of the dark matter in very early times, soon after the Big Bang, for cold dark matter is very small, you have lots of structure down to basically arbitrarily small scales. Whereas for hotter alternative dark matters, there tends to be some kind of small scale suppression, usually invoked to try to explain missing satellites or something like that at redshift 0. But it's also something that affects more broadly the intergalactic medium. And other alternative dark matters like fuzzy dark matter and so on generically produce a similar effect. So usually the way that people study small scale structure in the IGM is by looking at the Lyman-alpha forest. So there's been a whole industry of doing this for many years now. Large spectroscopic surveys with Sloan have sort of nailed down what this power spectrum looks like on kind of intermediate scales. And there have been some works to push this to higher resolution, either with very high resolution Echelle spectrographs or sort of moderate high resolution like X-Shooter. So the thing I want to point out here in this fairly complicated plot, so this is showing the power spectrum, sort of like the strength of fluctuations in that Lyman-alpha forest at various scales, going from large scales on the left to large scales on the right. And you can see that there's this characteristic turnover in this power spectrum. And this turnover is a lot stronger if you have warm dark matter. So these dashed lines here are showing the suppression of small scale structure due to, I believe, 2.5 keV warm dark matter. You'll notice, though, that actually the green models are turning over too, and there's a very good reason for this. Also, I should mention there's been a lot more recent literature, but this was the best figure I could find. But so the problem with using the Lyman-alpha forest to understand the intergalactic small-scale structure is that they're all pressure smoothed. So after reionization, the IGM is kind of generically around 10,000 Kelvin, and this means that at the mean density of the universe, the gas is sort of spread out, sort of squooshed out by about 100 kiloparsecs relative to the very clumpy dark matter distribution. And the Jeans length of the gas scales as the square root of the temperature. So if the gas were colder, there would be less clumping. The relevant scales would be smaller. So this is what the situation looks like at redshift of 3, where the Lyman-alpha forest is well studied. While the gas distribution, or while the dark matter distribution is highly clumped and has this lovely network of filaments, the gas distribution is a lot smoother. And so when people try to infer the nature of small-scale structure from the Lyman-alpha forest, they have to fight through this sort of haze of baryons being pressure smoothed and with a lot of forward modeling. Okay, but before reionization, the IGM was actually very cold. So here I'm showing a plot from Matt McQuinn's IGM review article from several years ago now, where the red line here is the evolution of the gas temperature since recombination. So universe recombines here, becomes neutral. It cools coupled to the CMB until about a redshift of 200 or so, and then just cools adiabatically, and the temperature plummets. And it keeps plummeting until the first sources of X-rays appear in the universe. So X-ray binaries from POP3 remnants kick in and rapidly fill the universe with X-rays and sort of modestly heat the gas up to tens or maybe hundreds or thousands of Kelvin. Then finally, reionization kicks in and everything heats up to over 10,000 Kelvin, as we saw before. So it would be really great if we could probe the small scale structure of the gas at these early times, because when the gas is this cold, so if the gas is 10 Kelvin or say 1 Kelvin instead of 10,000 Kelvin, that means we'd be sensitive to 1 kiloparsec scales instead of 100 kiloparsec scales due to that scaling of the Jeans length. So if we could study, the pre-reionization Lyman-alpha forest, we'd be in good shape. Of course, Lyman-alpha forest is completely opaque at these high redshifts, but as we've now seen in a couple of talks, you still see transmission in the proximity zones of high redshift quasars. So here I'm showing a zoom in on the highest redshift published quasar discovered by Eduardo Bañados. And you can see that there is this region here of a bit over 1,000 kilometers per second, where 0 here is systemic Lyman-alpha for the quasar. There's a region with transmission, and there's a region with structure. You can see some nice absorption features as well. And so potentially, we can use the information contained in this region to understand the structures in the very, very early universe. Now, of course, when the quasar reionizes that region around it, if it's carving out its own giant Stromgren sphere, it's also rapidly heating the gas by, say, a few tens of thousands of Kelvin. But fortunately, if the quasar has only been on for 10 to the 6 years, as Karna was showing, the gas actually hasn't had time to respond to this new heat injection. So here I'm going to show a movie of sort of low resolution in a 1 megaparsec box of the formation of structure in this small hydrodynamical simulation. Reionization happens at a redshift of about 8.3, and the baryonic structure just starts to explode. So it's all been heated to several thousand, up to 10,000 degrees Kelvin, and the initial sort of pre-reionization 1 kiloparsec scale just gets completely destroyed. But so I'm gonna go through this movie very carefully here. If we go back to when reionization occurs, okay, the gas is now hot. It actually takes a substantial amount of time before that structure really starts to disappear. So it actually lasts for a few tens of millions of years, maybe even up to 100 million years, after the quasar switches on and ionizes that gas. And so we can, in principle, then study the pre-reionization IGM by looking at reionization epoch quasars. And in fact, the structure we see in the proximity zone is quite sensitive to this. So here I'm showing, this is now a higher resolution simulation that I'll describe on the next slide, where I'm showing here a no reionization model versus a reionization happening very early model. So these are both at redshift 7.5, but here reionization occurred very early, and so the gas has expanded and blown up. If we now take skewers, many skewers through these simulations, stack them together, or stitch them together, and then run radiative transfer simulations, what we get is something like this. So because these boxes have the same initial conditions, we can compare them directly. And you can see here that the sort of hot versus cold models look quite a bit different. That the cold models have sharper, more opaque features in them. So this might be something that, for example, Huan Qing's density reconstruction might even be sensitive to, which would be really exciting. But I'm not going to talk about that because I didn't know about that until 10 minutes ago. So we can see here that there does seem to be a difference, that the proximity zones are sensitive to this very small scale structure, despite the fact that they've been thermally broadened by much larger than these very small scales. And I can answer questions about that later if people are curious. So what we study in this work are two primary ways that you could suppress the small scale structure that might be in proximity zones. So one, as I mentioned before, is X-ray heating. So if we have X-rays that heat the gas and slightly pressure smooth it prior to the quasar turning on, that could give rise to suppression of structure. And also warm dark matter. So if the dark matter is some sort of model that suppresses small scale structure, it can also then be imprinted in the proximity zone. We run these simulations quite carefully. So it turns out when you're modeling scales like this at early times, you have to take into account the drift velocity of baryons versus dark matter, both by inputting a velocity and also by changing the initial matter power spectrum. It's kind of a mess. But fortunately, there was a code available that let us do that easily. Now, what we get, so we run a few boxes exploring these different scenarios, so warm dark matter and X-ray heating. The warm dark, here I'm just showing, one skewer through all these simulations. You can see that there are variations between the black cold dark matter case and sort of these different warm dark matter and X-ray heated models. And moving on, because I'm running out of time. The question then, now that we've established that we can get these differences in the spectra from the small scale structure, can we actually detect this observationally? And so with this sort of observational setup, maybe like an XQR2 or XQR10 or something in the distant future, near distant future, we can compress those proximity zone spectra into some of people's favorite statistics. For example, the power spectrum, looking at the strength of fluctuations, and just the PDF of the flux in pixels inside the proximity zone. And we see that indeed the cold dark matter, the cold dark matter case seems to be distinguishable from these sort of more extreme cases. This is sort of 2000 Kelvin X-ray heating and 5 keV warm dark matter in the yellow and blue respectively. And on this plot, the blue and yellow are overlapping pretty severely, but they're both there, I assure you. If we now perform inference from these spectra, this is now a reasonably challenging procedure to do, because we know that the likelihoods are not particularly multivariate Gaussian, so we have to do a little bit of trickery in order to get rid of that. But we find that in principle, with a sample of 10 redshift 7.5 quasars with moderate resolution and reasonably high signal to noise, we should be able to constrain warm dark matter models up to about 10 keV. And actually, perhaps more interestingly to people who don't believe in warm dark matter, we'd be sensitive to say 1000 Kelvin of X-ray preheating. This is something that 21 centimeter observations are very interested in. And so we think we could actually constrain this using these Heisey proximity zones. And I'll just end here showing off the summary slide, and I'll take questions. Thanks.
Thank you very much. We can all. Okay, questions. So we have a few minutes of questions. First question: if quasars form in the highest mass halos, reionization in the region around the quasar may have started much earlier. Should that be a caveat for your conclusion?
Sorry, I was reading another message that apparently people could see this some build thing on the side.
Right. Will the quasars in high density peaks, so reionization may happen earlier? Would that be an issue for you?
Yes, so this is definitely an issue. So this is something that of course is very difficult to simulate with only a 1 megaparsec box. This is something we plan to explore first by just expanding the boxes to be bigger, and then later looking into potentially doing some kind of a zoom simulation. The problem here is that to really explore the whole proximity zone, you need to get to scales of, say, a couple of tens of co-moving megaparsecs. So your high resolution part of your simulation needs to be 10 or 20 megaparsecs, and you need to resolve down to sort of 1 kiloparsec scales at the mean density. So I don't mean like with lots of refinement. I mean at kind of your base grid needs to resolve 1 kiloparsec. And so this is currently outside of kind of our current capabilities with big supercomputers. I think it'll become more possible in sort of 5 to 10 years. There are new exascale machines coming online in the US that may make this possible. But it should make a difference.
Okay. And do one more question. Can you resolve the degeneracy between, in fact, of warm dark matter and X-ray heating?
So currently we think we can't. And so I think we would be more comfortable with saying, giving a constraint on one versus the other, or one at fixed value of the other. Currently, like just with the statistics that we've looked at so far, so just the flux PDF and the power spectrum, they seem to be pretty degenerate. Not exactly degenerate, so some kind of joint constraint may be possible. But that degeneracy is probably the biggest weakness of this. Although a detection of either is still interesting, and so then it just becomes a matter of interpretation of which Do you prefer that cold dark matter isn't real, or do you prefer that the universe is X-ray heated?
Thank you. There are more questions in Slack that you can answer later.